So, I'll begin with a word of prayer before I forget. Dearly Father, we thank you for the weekend and for the week's about to start. We just pray that you'd be glorified in what we do. I just pray that students would just be able to wrap up their studying for test 1 tomorrow, that they could just do their best, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, so you guys have any particular questions? I can run through the math battle if you want, but yeah.
Is there a fast way to find the torsion?
There is no fast way to find the torsion, no. Unless you happen to observe that your curve is planar, in which case you know the torsion's 0. But even so, depending on the way the problem is stated, I might still want you to show me that. Although if the curve is planar, the torsion working out to 0 will be easier. Like, you will see it coming as you get the binormal being like a constant vector. Right? So if the torsion is 0, the binormal will work out to be a constant vector. But that could happen in a very convoluted way. You know, like it could happen because of various cancellations of functions and things. So, anyway, this much is true. An error at the start of a TNV problem can make it infinitely more complicated, right? Like if you don't cancel the thing inside the square root, that is the gift that keeps on giving for the rest of the problem, right? It will make it much harder than it actually is. So that's just the nature of those problems. Problem, goodness, about to start coughing. Part A is notice some of you guys missed unit vector, right? So you're right, cross product of the u and v gives you a perpendicular vector, very good. But the word unit vector means you have to divide by the length to make it into length 1 vector, right? So some people missed that. More people had a wrong cross product. That's more troubling to me. You need to fix your cross product if you haven't already, like that matters, obviously. The parallelepiped of 3 vectors, you calculate the triple product, right? So the dot product of the cross product, that'll give you the volume of the parallelepiped. What else geometric could we calculate from the cross product of 2 vectors? What would it tell you? What's the magnitude of the cross product? Is what, the area of the parallelepiped? To the area of the parallelogram with sides AB, right? What if you want to find the area of the triangle with sides AB? You just do what? Divide by 2, right? Because it's 1/2 the area of the parallelogram by basic geometry. Some of you are working way too hard on this angle here. I don't know what happened there. Some of you just ignored the circle obtuse or acute or right question there. I'm going to assume that was an oversight. Let's see here. Yeah, so A dot B being 0 is of course orthogonal. A cross B being 0 is a measure of 2 vectors being parallel. Of course, they could also be antiparallel. More generally, A cross B being 0 means that the vectors are collinear. The third one, the last one here, A cross B dot B, that's a sensible thing. We're taking a cross product of 2 vectors, that gives us a vector. We're taking a dot product with another thing. Dot product of vectors makes sense. And yes, of course, by construction, A cross B is perpendicular to B, so that's always true. But the one right above there, the cross product of 2 dot products, that's just utter nonsense. You cannot take the cross product of numbers. It's not something we have defined, nor do we intend to. So for this, you guys, a lot of you have given me what's in blue as the answer, and that's a nice calculation, but that's not the answer. The answer is the red. So, like, a lot of people in here have the correct work, but you didn't conclude. You didn't find the resultant vector, you know. That's an easy thing to remedy if I was to give that problem on the test, right? But not a big deal. Man, this problem's got so much in it, right? This one here, wow. It's like so much going on, right? So first of all, you got to parameterize the line that goes through the point P and Q, which is done here. And a lot of you did that correctly, I think. Once you do that, you can see the direction vector to your L2 is 3 minus 1, 1, right? And if that's not collinear with the line that's given, which is where R1, right? So the direction vector here is 1 minus 1, 3, differentiating. That is not collinear to 3 minus 1, 1. Therefore, they're not parallel. They might be intersecting, they might be skew, right? And how do you figure that out? Well, you look for the intersection. So you set R1 of S equal to R2 of T and work it out. So we've worked this. I did a problem like this in class, actually. There was one in your homework, the Jenin Ninja problem. Remember that one? Where I have the last sentence flipped, the meaning of Jenin and Jonin. Sorry about that. Maybe the Jenin was Naruto. Leave me alone. Let's see here. So anyway, so you solve these equations and out pops t equals to 0, and then you can go back and see s equal -1, which means indeedly doodly you do have a common point to both lines, which means they intersect. So yeah. So if you're wondering, this is an old test of my brother. My brother's a math professor at Appalachian, and he writes short tests which have everything under the sun on them. And I think they're ideal for your math battle because they give a really good synopsis of this particular part of the course, right? My test is not the math battle, though, all right? My test is more like my old tests. If you look, I have one posted, right? So you can look there. Anyway, so we can keep going through this, and I guess I should for a little bit. The equation of the plane containing those 3 points. This is a standard problem. Almost every single Calculus 3 first test I've ever given has this problem on it. Given 3 points, how do you find the Cartesian of the equation? Cartesian equation of the plane that contains the 3 points. Simple. You find the vector which connects one point to another point, and that same point to the third point. That gives you 2 vectors which are tangent to the plane. You take the cross product of those 2 vectors. That gives you the normal to the plane. And then you pick any of your 3 points and put together the plane equation. Like that. Done. So it's a standard problem. You shouldn't be surprised by this problem if it's on the test. You know, the area of the triangle, again, it's half the magnitude of the cross product. So you've already calculated the cross product to set up the plane equation, so that should have been a gift, right? Any questions about number 4? So I often give a velocity or acceleration or position problem on this test. You need to know the relation between velocity, acceleration, position, speed, right? How do you calculate arc length? How do you calculate distance traveled? Same question. The arc length is the distance traveled for the whole curve, right? So like if you go in a circle, the arc length is 2 pi r, the distance traveled is 2 pi r as well. That's our definition of distance traveled. So. Let's see here. Well, anyway, I can keep going through the math battle, but I'd kind of rather take your questions. There are some neat formulas at the end of this, right? So one of the questions inevitably is like, is there any other way to calculate T and B? No, you need to calculate it as I calculated it. You face the music. You start with the position vector, you differentiate, you get the velocity vector. You normalize that to get the unit tangent. You take that, you differentiate that, that gets you the derivative of the unit tangent. You normalize that, get to the normal. Once you have that, you take the cross product of T and N to get B. That's how you do it. To calculate the curvature, you take 1 over the speed times the magnitude of T prime. That's the curvature. The torsion is minus dB dt dot the normal divided by the speed as well. So like, these are all straightforward, but sometimes tedious calculations. But then again, you have a 75-minute test, right? Where you have probably 12, 13 questions, something like that. So am I going to ask a torsion problem? Am I going to ask a torsion problem where the torsion is like some super complicated function of time? Obviously not, right? I would have to devote like, a lot of the test time. Well, that was a lot of this test time. If you look carefully, there's no other hard problem on this test. I don't think. Is there? It's unlike my brother to ask more than one hard question on a test. So, oh, you're thinking, it's funny because this is actually complicated. Wait a minute, this is not complicated though. Hold on a second. This one has constant speed, right? Ah, but the next one, my brother was also kind, wasn't he kind? There was a gift given in the next problem which made the problem a little bit more manageable. And so if you know these formulas, right, like the curvature is the magnitude of the velocity cross the acceleration divided by the speed cubed, right, and the torsion is given by this formula, right? So if you knew these formulas, you could use those to calculate curvature and torsion. Did we derive those? We have not. So do I expect you to use them? Not without deriving them, right? So, yeah. So anyway, if I was to expect you to use those special formulas for curvature and torsion, you know, I'd have to have a problem before that problem where you actually derived those formulas. Which is not impossible, right? You could derive those formulas from the Furness-Ray equations, for example. Let's see here. Of course, we've talked about the tangential and the normal components to acceleration. So, I mean, these. So all you're looking at, I mean, don't be deceived. All this is the unit tangent dot the acceleration. That's all that formula is. Because r prime over the magnitude of r, that's big T. That's big T dot A. That's exactly what we did to calculate the tangential component of the acceleration. Now this over here is a deeper magic. We don't have that formula. That's true. So if we were going to use it, we probably should derive it. But anyway. So guys, do you have questions about like mission 1 or anything in there? Anything particular that was, yep.
You mentioned something about us having a little bit of gap over the integration in respect to arc length.
Yeah.
Can you do an example of what that would look like?
Tell you what, let me just be honest. I am not going to put an integration with respect to arc length problem on the test. So that way we won't burn any time today on that. We will get back to integration with respect to arc length like soon enough. Now, could there be an arc length integral? Sure, that's a possibility, right? So I could show that. Let me do that. What if you were going to calculate the arc length of like because I'm dissatisfied with the amount of homework I had on that, so I feel it's unfair to put it on the test at the moment. It's poor design on my part. But here's one. If we had r of t was like, oh, I don't know, t cos t, t sine t, e to the t, we can calculate the speed and set up the arc length integral, right? And try to be as simple as possible. How does that go here? So let's see here. dr dt is, let's see here, cos t minus t sine t plus t cos t e to the t. And then when I calculate, you know, v dot v, take the dot product with itself, I've got cosine t minus t sine t squared plus sine t plus t cosine t squared plus e to the t squared, right? And how does this all work out? Well, that gives us a cosine squared minus 2 sine t cosine t times t. I'll just write the t first. Plus t squared sine squared t. And then plus sine squared t plus 2t sine t cosine t plus t squared cosine squared t plus e to the 2t. Forgive me for putting two pluses. It is my way. Of course, there's some vast simplifications that happen here, right? Our formula for speed squared has what? We've got what? We got like these two guys give us a 1, right? And will these be canceling? Woohoo! Right? And this is kind of generically a pattern you should see anytime you've got sine and cosine multiplied by some same function, right? If you have the same function multiplying sine and cosine and you look at the speed, this kind of cancellation will happen. As far as I can remember, it always happens. Now these two here give us a t squared, and we got plus e to the 2t. So lo and behold, the arc length, s, we could integrate from 0 to t of the square root of 1 plus, let's say, tau squared plus e to the 2 tau d tau. There you go. That would be the formula for arc length as a function of time if we base it at 0. Yep.
How would you reparameterize that curve with respect to the function?
Oh, yeah, I could not actually carry out the reparameterization in terms of an explicit algebraic formula because I can't integrate that. However, theoretically, you can say that this is, s, this is s of t, and because s of t is an increasing function of t, it has an inverse, and as such, I can write the arc length parameterization of this, right, as equal to r of s inverse of s. So I can only do it theoretically, but like pragmatically speaking, I can't find the formula to like solve this equation for t. Like we were able to solve for t in 2 different cases in the homework, right? Like in class we had one where it was just like, s was equal to 3t or something like that. We solved for t is s over 3. Woohoo! There was one in the homework that was more interesting. It was like, let me see if I can find that problem. Have you guys seen through that problem yet? There's a, oh man, come on. Where was that thing? Can you guys help me out? I think it was mission 1. If I can find it. Where'd that thing gone to? Maybe it was mission 2. I'll find it eventually. It will not escape me. Where'd that thing go? Oh man, I had a problem where it's a line, right? It's a line in disguise, but it's got like it's like a t cubed or something. What problem is that? I'm just not seeing it at the moment. It's not popping out at me. You guys remember the problem, but you can't tell me which one it was, huh? I guess that puts us in the same boat. Well, what?
Was it 25, mission 2?
Yes, 25. Thank you. Yeah. So Violet, this is a good one for your question, right? So here's one where we could actually carry it out, right? So this is a very silly parameterization of a line. Or it could just be a parameterization of a line where you're physically like, you have a force on the particle which is increasing linearly with time, giving you, right, an acceleration which is actually linear in t, truth be told. Anyway, however you want to look at it, it's a line with direction vector 1, 2, 3, and the arc length as a function of time happens to be given by 3t cubed here. I could actually do the integral, and I can actually carry out solving for t here, right? t cubed is s over 3, and then, so my point to you is I can only actually ask you to reparameterize the curve with respect to arc length in as much as it's possible for you to actually solve the arc length integral and then invert it, the formula, right? Like, that gives me t cubed is s over 3. And so that was just, I was able to just substitute that in because my original formula had like t cubed in each thing, so I just plugged in. I plugged in s over 3 for t cubed. But if you want to see it a different way, we could have solved for t as the cube root of s over 3. When we could have plugged the cube root of s over 3 into t every place it was, and then when we simplify the cube, we would have got back to this formula, which is all I'm saying. So, does that answer? Yeah. I like the problem right before that. That one was fun. What do you think? What do you guys think of this one? Well, not right before. I guess right before that, that's an interesting problem, but it's kind of, you know. The point of this problem is if you've got constant vectors, you can pull them outside the integral and just focus your integration on the scalar part and just do it as if these are numbers. So vector calculus is very nice in that regard. The problem before was an invitation to review the binomial theorem. You may not have realized that, but so essentially, if we differentiate twice, we get just like a squared plus 2ab plus b squared. If you understand that the function alone is kind of like the 0th power. If you think back to Taylor's theorem, right? Like the f parenthesis of a. When we put 0 inside the parentheses, it's just function evaluation, right? So the same pattern here is holding, and you can prove that if you calculate the kth derivative, it works like that, right? So if there's a problem like this, should you be dropping to components, or is the way to solve that to use the properties of, like, you know, vector calculus, you know, the calculus of paths that we've talked about? We should use the properties, right? Unless, of course, the whole problem is to prove that the product rule for the cross product holds, right? That's a possible problem on the test. It's kind of boring because it's just like pretty straightforward and gory. Maybe the prove the product rule for the dot product is a nicer problem, right? We actually did that one in class in the plus dot dot notation, I think. Or maybe I don't know, but let's see here. Any questions, you guys? You guys got no questions. You're ready then, huh? Everyone's got their formula card prepared? It's in your head? Well, okay. Ostensibly, that's hard to take away from you. I mean, I guess if it's taken away from you, it's a bad day. Let's see here. So as you look at problem 26, like suppose I give you something that looks like problem 26 on the test. What should you think in your mind when you see this formula? We've done this a few times now, right? You should look at it and you should go, huh, you know, it's got sine and cosine. They're both multiplied by the same number. And it's got t sitting in the other variable. And well, he's added some numbers, right? That just moves the curve around, right? Adding the 2, and the 1. That just shifts the curve. It doesn't really change its t and b stuff. So you should just take a look at this, and you should know what you're up against. You should realize at the start of this problem, that's a helix. It's got the pattern of the helix. Now x and y and z are shuffled from what we did in class, but it's a helix, right? So you should have some expectations of a helix problem, right? Like when you work out the speed, should it be a function of time? No, it should be a constant speed curve, right? You should see that. If you've got cosine squared and sine squared unsimplified, and you keep working with that, that's on you. All right, that's on you. Do not do that in this problem. You know, like make sure that if there's something like this, you need to do the pre-calculus and simplify that. If you don't, I'm sorry, but this problem becomes like way, way harder than it actually is. And it will like kill the rest of your test if you don't make that simplification. Pre-calculus matters. It matters a lot. Anyway, just saying. And then the other thing, of course, is we know that we've experienced before the curvature and the torsion of a helix are constant, right? And of course, you have a formula card, right? So you could put the formulas for curvature and for torsion on your formula card, right? And it is true, I will give you some partial credit for just putting the right formulas down for curvature and torsion on the problem I put on the test. But it will just be partial credit. I do expect you to actually go through the calculation. It is not just, you know, oh, it's a helix. I'm supposed to plug and chug these formulas. That's not what this class is, right? Like, you are supposed to explain the calculus. So, but anyway, here's me at the end of the problem saying, hey, by the way, it does fit our generic formulas for a helix, because while I worked those formulas out for like a helix probably in the z-axis, wrapping around the z-axis, there's nothing stopping us from pointing it in a different axis or shifting it around, and none of those things change the curvature or the torsion. Let's see here, any other questions? I mean, sorry about the last problem. I guess I should say that. Like, man, if you actually calculated, if you really followed the verify through, woo, that would have been quite beastly, right? So, and if you did that, that's good for you. That means you've gained dexterity in calculation. It will pay off on the test. It will, yeah.
Out of interest, does the acceleration in the normal direction have a non-radial
Ooh, I don't.
in cylindrical coordinates?
In cylindrical coordinates.
Transform that into cylindrical coordinates, it makes everything super simple. Like the acceleration is 2 in a certain.
Ah, so your question is, what if you do this problem in cylindrical coordinates?
Because I assume that it would be negative r hat for the normal.
Let's see. So you have, yeah, I mean, you have r equals to, well, okay, fine, yeah, you've got, well, I mean, I guess you could say r equals 3, theta equals t squared, z equals 2t plus 1. Now, we've not really done anything quite like that, so I'm not sure where to go from there. I suppose if I had expressed, see, in order to make use of this, I would need to oh yeah, I can't do that right now. Yeah. No. No. You, no. No. That is opening a box I cannot open in the day before the test on the review day. Yes, sir. Sorry, what? Well, will there be a problem that explores velocity, position, acceleration? Sure, that might happen. Is there going to be a problem where you need to know the relation between the tangential and the normal parts of the acceleration? Totally possible. Would there be a problem on the test where I actually made you verify that A was AT and ANN plus ATT like in this problem? No. That's too much. None of you can finish that calculation in 75 minutes. I don't think I can. Well, okay, maybe I could, but I would have to be really awake, and somebody would have to pay me some money. Let's see here. Let's see here. So are you guys good on parametrized surfaces? This is not a big part of the test. It's kind of more like the trivial pursuit part of the test, but suppose you wanted to, suppose you're given, okay, suppose you were given formulas. How would you check whether or not they're actually a legit parameterization for a surface? Like, if I tell you, you know, x equals to, oh, I don't know, cosine theta, sinh phi, and I tell you y is equal to sine theta, sinh phi, and I tell you that z is equal to, you know, 3 cos phi. These are, you know, parametric formulas for the parameterization of a surface. Would you have a chance at figuring out what the equation of that surface was? See, I don't think that's a question I would ask you guys in the form I just asked it, without giving you like a significant like push in the direction of what is the answer, right? So if I have a question like that, it would have to be in like a multiple choice format, where I had like these formulas, and then I had, you know, like, oh, I don't know, is that x squared plus y squared equals to z squared? Is it x squared plus y squared minus z squared? Is it equal to 1? Is it, you know, x squared plus y squared minus z squared over 9 equal to, since I'm spending the most time on this, you know this is the answer, you know, minus 1. And then, you know, maybe I'd have like 3 different equations, and I'd have 3 different parameterizations, and then you could just match which one goes with which. That frees you of the super hard part, which is like creating the parametric formulas from the thin air, right? I don't think I should really expect you to create the parametric formulas in this test, because I haven't spent that much class time on it, and you haven't had a lot of homework on it yet, right? But if I give you multiple choice, you should be able to kind of play match game, right? Like, how would this go? You should be able to see that x squared plus y squared is equal to sinh squared phi. And then, of course, we know that, you know, cos squared phi minus sinh squared phi is equal to 1, which tells me that apparently z over 3 quantity squared minus x squared plus y squared is equal to 1. Which, at that point, you can be like, oh, wait a minute, it's that one, right? So if I had 3 sets of formulas or 4 sets of formulas and then, you know, corresponding equations, you should be able to basically just play match game there, right? If I was to put a problem like that on the test. I have put a problem like that on this test before. I'm kind of on the fence about whether or not I'm going to do it this time, but, to be honest. Now, on the other hand, I do think it's more fair to ask you to parameterize a curve, right? If I asked you to parameterize a curve of intersection, that is something you should be much more able to do, because we have allegedly done that in Calculus 2 already, right? So that's in some sense a review. What if I ask you to parameterize, like, you know, x squared minus y squared over 3 equals to 1? How would you do? Parameterize this for, say, x, you know, greater than 1. You should just go, oh, I know what this is. This is a hyperbola. So I write down x is equal to cos t, and I write y is equal to the square root of 3 sinh t, because I know if I do that, then when I plug those in, I get cos squared minus sinh squared. Woohoo! And by the way, by construction, this is greater than, I should probably say greater than or equal to 1, just to make it, you know, not nasty. There we go. That's how we parameterize a hyperbola. So I gave you parametric formulas for an ellipse, a hyperbola, and of course a line, right? You should be ready, willing, and able to parameterize lines. The only other thing I would say you should be able to parameterize, because we've had a homework problem on it, and I've talked about it in class a fair amount, is how to parameterize a surface. What kind of surface do I expect to be able to parameterize? How about the plane, right? If you got a plane, it's got points P, it's got points Q, it's got points R. That is kind of the one surface I do expect you to be able to, with authority, parameterize at this point. We have had a homework problem on that. I've had you guys explore how to get from that parameterization of the plane to the Cartesian equation of the plane, right? So we've spent more time on that. That's a more reasonable question for test 1. All right? Do you guys know, and that's, I think it's in the homework. It's like, what, problem 4 or something, problem 5, something like that. Anyway, listen, if I have slighted your team in my grading of the math battle, do let me know. I was grading it in a hurry, and I may have overlooked something. I'm happy to give you those points back. And I hope you guys do better on the next one. I think you will, right? It's 25 points. So, but I also will try to smooth the teams out a bit. next time I will choose different captains, let's say that. So anyway. Hmm? Oh yeah, you guys can take, absolutely, you can, if you guys want to take pictures of the math battles for each other, that's fine. Yeah, that's yours to keep. I don't keep them. And, oh yeah, the answers are posted in Canvas. Oh, also, I have not talked about the quizzes today, but that's not because they don't matter. Like, I do usually think about quizzes a little bit when I'm making tests. So anyway.